So today we are going to talk about absorption and refraction of color. First, let's talk about light. So what is light? In Physics 143, we have talked a lot about light. But just to refresh your memory, light is an electromagnetic wave that has a special wavelength, frequency, and speed. In physics definition, light does not have to be visible light rays, like sunlight or flashlight you can clearly see. Like all types of EM radiation, gamma rays, X-rays, microwave, and radio rays are also light. In fact, only a very small portion of electromagnetic radiation is the visible light we see in everyday life, as you can see in this picture. The behavior of EM radiation depends on their wavelength and frequency. As you can see, visible light only exists with 380 to 700 nanometers of wavelength, and with frequencies around 1 × 10 to the 14th to 8 × 10 to the 14th cycles per second. Since wavelengths and frequencies are inversely proportional to each other, the wave will have greatest frequency has the shortest wavelength. In this lab, we will focus only on visible lights. Now, how does this correlate with colors of objects we see in everyday life? When the light ray hits the plane of incidence, some light is absorbed. And some lights are reflected. Like what we learned in class, the rule of reflection tells us that the angle of incidence perpendicular to the plane is the same as the angle of reflection. However, besides the angles, the object also absorbs certain colors depending on its properties and material. And the reflected ray contains only the colors object did not absorb, which are the colors our eyes perceive and identify with. For example, when you see this pink highlighter, it appears pink to you because it absorbs all the other wavelengths of light and only reflects pink light at certain wavelengths. If an object that absorbs all wavelengths of color, it will appear black. Objects that reflect all wavelengths of light will appear as same color as the light source. And this is why ocean is the same color as sky. Like what I said, a light ray consists of many different colors of different wavelengths. Light can interfere when there is only one slit. When these rays meet at one point, they all have different phases. This interference pattern is called diffraction pattern or single slit pattern. Like what we learned in class and in many labs. Since diffraction can split a single white light ray into many different wavelengths of colors, you might ask if we can combine all the colors and make white color. This is true for only additive colors. Let me introduce you the 3 primary colors: red, green, and blue. Many of you probably heard of RGB, combining various amount of primary colors can make any color you want, and this is how our computers are able to create so many different colors. On the opposite end of spectrum, there's subtractive colors: cyan, magenta, and yellow, as known as C and Y. This means that one begins with white and ends with black as you add more colors. This works for various pigments under the white light, like our printer. If we mix C and Y inks on paper, they absorb light and our eyes will perceive black. However, in terms of what we see in everyday life, you might find CMY color model more useful in real life. Back to my previous point, objects reflect light of their own color because it acts like an barrier that blocks all the other colors and only let their own color's wavelengths to be reflected. What does this sound like for you? That's right, subtractive colors.